All right, today's video is about light waves. We're basically just going to learn some of the fundamental basic things you need to know about light. Here we go. So light is just one type of electromagnetic wave. So before we learn about light, we need to learn about electromagnetic waves. So here are some properties of all electromagnetic waves. All right, so first of all, they're caused by vibrating electrical charges. All right, the result is a transverse wave. Interesting side note, light waves actually vibrate in two directions. There's an electric portion that vibrates vertically, and a magnetic portion that vibrates horizontally. So you've got three axes. The light is traveling along the z-axis, there's a vibration along the y-axis, and another vibration along the x-axis. So anyway, they're transverse. That's what you need to know. Let's see. The amplitude of the wave is going to determine how bright the light is, or how intense the light is. And along those lines, all the equations that we learned last chapter still work. So that means that the intensity still is inversely proportional to the distance squared. It means we can still use velocity equals frequency times wavelength. It means frequency is still the reciprocal of period. So all those equations that we learned last chapter still work when we talk about light. Okay? Probably the biggest difference between electromagnetic waves and mechanical waves that we talked about last chapter is this third point here, or what is this, fifth point here in purple, which is they do not require a medium to travel through. Okay? Light waves can travel through a vacuum. You see that because you can see the sun, right? But that said, their speed is still determined by the medium it travels through. And what happens is light travels slower through mediums or media, which are more what we call optically dense. All right. So the least dense medium you could have would be a vacuum, right? Empty space. And the speed of light through a vacuum is 3 × 10⁸ meters a second. So that's 300 million meters per second. It goes a teeny bit slower through air. The difference is so small, though, that for most calculations, people just tend to use 3 × 10⁸ meters a second, just for simplicity. All right. But as your medium gets more dense, as you move towards water or glass or diamond, the light does slow down fairly significantly. All right. A quick comment about this number here. This guy, that number up on the top there, 3 × 10⁸ meters per second, is referred to as the speed of light. So, and we refer to it by the letter C. So you will see sometimes C equals 3 × 10⁸ meters per second. That is a science constant, okay? In the equation, E equals mc squared, that's what C is. It's the speed of light, okay? So there you go. All right. Also worth noting is this. Light is really fast. Okay? Like I said, it travels 300 million meters in a second. In a year, in 1 year, light will travel 9.5 × 10⁵ meters. That's 5.9 trillion miles. 5.9 million miles. The main reason I comment on this is a light year isn't an amount of time, it's a distance. A light year is the distance that light travels in 1 year. Okay? That's one of those things that doesn't really fit well into any section of the notes, so I put it here. All right? I was going to ask if you have questions, but I wouldn't be able to answer them if you did, so I'm going to move on. All right. Now, the frequency of an electromagnetic wave determines what kind of electromagnetic wave it is. All right? And so it turns out that we have what's called the electromagnetic spectrum. All right, and the spectrum here is set up so that it goes from small frequency to big frequencies, which means that this end of the spectrum has big wavelengths and this end of the spectrum has small wavelengths. Okay, so an electromagnetic wave, or the electromagnetic wave that has the smallest frequency, is called a radio wave. And that's a little weird. Some of you might be going, well, I thought radio waves were sound waves. and they're not. Your radio actually works using an electromagnetic wave called a radio wave. And then the function of the radio is it converts the radio signal into a sound wave using the speakers. Okay? So anyway, the smallest frequency electromagnetic wave is a radio wave. As your frequency increases, you hit microwaves, infrared, visible light, which incidentally is broken up down here. This is visible light. Okay, it consists of everything. Oh, sorry, it's not right. This is visible light. Visible light consists of all the colors from red to violet, right? Roy, red, orange, yellow, green, Roy G, blue, indigo, and violet. All right, I don't care if you put indigo in or not. It really doesn't matter to me. So visible light is what you think of when you think of light. All right. I'll talk about that more here on the next slide. All right. As your frequency continues to increase, the next biggest frequency is ultraviolet. Ultraviolet light is a light wave, but it just has a frequency that's so high that humans can't see it. Okay? Think about it. Last chapter we learned about infrasonic and ultrasonic. Infrasonic was a frequency that was too low to hear. In the same way, infrared is a frequency that's too small for humans to see. All right? And then ultrasonic was a frequency too high for humans to hear. Ultraviolet is a frequency too high for humans to see. Okay? So in the same way that sound determines, frequency determines, the pitch of a sound, the frequency of a light wave determines what kind of light wave it is. All right? As the frequency keeps increasing, the next one you hit is X-rays, like you would use to take X-rays of your body, and then gamma rays, which would create incredible hulks. So there you go. That is the electromagnetic spectrum. You should know this order. It's important. Okay. There we go. I think that is all I need to say about that. This picture was stolen from this website down here, incidentally, which I guess I should uncover for copyright purposes, right? There we go. So, thank you, wordpress.com. Okay. All right. Now, everything that we're going to learn in this chapter applies to any kind of electromagnetic wave. But that said, a lot of times I'll just use the word light to refer to an electromagnetic wave. Okay, like I just said, ultraviolet light. Okay, referring to an electromagnetic wave that is ultraviolet. Okay, so anyway, we're going to learn more about colors soon, but for now what you should know is that white light can be broken up into all of the colors of the spectrum, right? And I just kind of showed you that. I think what I did not emphasize is that these colors combined make up white light and vice versa. If you've ever seen the Pink Floyd album cover for Dark Side of the Moon, you know that white light can be converted into the colors of the spectrum. So here you can see there is white light here that I've just underlined with green going into a prism, and the prism causes the light to split up. We'll talk about why that happens later on into the different colors of the rainbow. Okay, so that's just white light being broken up into the different colors, and I'll show you a demo of that in class. All right, so all right, and then black, the other part of that screen there, is the absence of all colors in the spectrum. When you see black, you're seeing that because there is no light, at the part you're looking at hitting your eyes. We'll talk about that here in a minute. Okay, so when light hits an object, this slide is really important, and I am now a little frustrated that I didn't make the font bigger. Let me make it. All right, so there you go, bigger. All right, so when light hits an object, at least one of the following three things is going to happen. So number one, if the object has particles, like atoms or molecules or whatever, whose natural frequencies match the frequency of the light hitting it, then the particles are going to resonate. We learned about that last chapter. And what that causes them to do is it causes the particles to vibrate with a bigger amplitude, which creates heat energy. It takes the light energy that's hitting the object and converts it to heat. All right, this is why black t-shirts are hot, right? They absorb all of the light because black is the absence of color, right? So it's absorbing all of the light that hits it, converting it to heat. Okay? When that happens, we say that those frequencies are absorbed. All right? Now, what you see is determined by number 2. Any frequency that doesn't get absorbed is what gets reflected. Okay? The colors that are reflected determine the color that you see when you look at the object. So either the color is going to get absorbed or reflected. Okay? If it gets reflected, that is the color you see. And then thirdly, some objects are transparent. They're see-through, right? Like glass or clear plastic or something like that. If that's the case, it's also going to transmit any frequencies that don't get absorbed. Okay? Basically, if it's transparent, it'll transmit and reflect the same colors. Okay? So that's why if you put blue cellophane over a light, like maybe you're having a party and you need, mood lighting or something, so you put blue light over the light bulbs, it's going to make all of the light in the room look blue, right? Because blue light gets through the blue cellophane. Okay, so this is probably easiest to see by doing an example. Again, we're going to learn more about colors later on, so what you're about to see here is a little bit sloppy, but it's a step in the right direction. It's about halfway. So here we've got a red hat. So what I'd like you to imagine is white light. Remember, white light is actually consists of all the colors of the rainbow. So here's our light bulb over here. White light. Okay. So the white light is going to come out of the light bulb and hit the hat. All right. Now, since the hat is red, what that means is if you're over here looking at it, it means that red light must be boom, boom, reflecting off of it so that you see red and you think, oh, there's a red hat. This is supposed to be you thinking. Oh, you see red, right? And since you don't see orange or yellow or green or blue or indigo or violet, that means that those colors are all getting absorbed. Okay, so those other colors that we don't see just get converted into heat. Okay, so that is the deal with the red hat. Now, for a clear blue water bottle, what's going to happen is, same idea, you're going to have your white light coming. Oh, that is apparently, let me see, let me do this real quick. Okay, so there's our light hitting it, right? And if you were looking at it over here, here's you, hello, you're going to see blue, right? That means that blue, which one's blue? This one. The blue is going to get reflected. And so you're going to think, oh, sorry, I wanted to write reflected. The blue gets reflected. So you're going to look at that and you're going to go, oh, that looks blue, right? Now, since it's transparent, that means blue light is also going to get transmitted. So if you somehow put a flashlight behind this thing, the only light that would come through the water bottle would be blue. So again, if you're over here looking at it, you would again think, oh, that looks blue light, right? Being transmitted through it. Now, what happens to the other colors? Well, when you look at that water bottle, you don't see any of these other colors. So the red and the orange and the yellow and the green and the indigo and the violet all get absorbed. Okay? So, you see what does not get absorbed. Okay? Now, interesting side note, you can't get sunburned if you're indoors. If you're behind glass, you can't get sunburned. All right, and the reason for that is this. Oops, that's not what I wanted to do. Glass, regular old clear glass, is transparent, right? So what that means is that any color that goes in also comes out, right? So your light is going this way, all of this gets transmitted, so any color that came in through the window is also going to go out through the window, right? That's why you're able to see green trees behind this window here, right? There's green trees there. You can see that because the green is going from the trees through the window to the camera of the person who took this picture. It turns out, though, that if you were standing inside, here's you looking out at the trees, thinking, right? So there you are, thinking about trees, right? It turns out you cannot get sunburned, and the reason for that is ultraviolet rays, due to the makeup of glass, ultraviolet rays cause sunburn, right? So those ultraviolet rays actually get absorbed. I'm going to enter my telephone. Okay, sorry about that. So the UV rays get absorbed. So what that must mean is there must be particles in the glass that have a frequency that matches the frequency of ultraviolet light. And so that will cause the window to warm up a little bit. All right. So why would you see white? Suppose you're looking at a t-shirt. This guy here is wearing a white Ghostbusters t-shirt. So what that means is the white light is coming along, right? Oh, there it is again. All right, whatever. So the white light is hitting it. So since you're looking at it and seeing white, like here's you, right, looking at the Ghostbusters shirt and thinking, oh, there's white. What that must mean is all of the colors must be getting reflected. So Roy G. Biv, right? Because white light is made up of all of these colors combined. Okay? So there, nothing is being absorbed, which is why it's good to wear white in the summer, right? Because it doesn't absorb any colors and it doesn't get as hot as if you are like this girl down here, whoops, wearing black. For her, here comes all of the white light coming in to hit her, right? Oh, that's not what I wanted to do. So here comes the white light, or the white light, right? Here, black is the absence of color. So over here, you're looking at the shirt, all of these colors are going to get absorbed. Nothing gets reflected, so you look at this and you go, oh, that's a black t-shirt, right? Okay? So the white looks white because it's reflecting all the colors. The black looks black because it's reflecting no colors, which is why a couple slides ago I said black is the absence of all colors in the spectrum. So when you see black, you're just seeing no colors being reflected. All right, so we're going to learn more about these colors and how they work, and we'll talk about primary colors and stuff. But at this point, what I want you to understand is that sometimes colors get absorbed, sometimes they get reflected. If the object is transparent, anything that gets reflected also gets transmitted. All right, so I think that is it. That is it. There you go.